So I'm going to bring the x squared to the other side and solve for it. So if I take this over here, I'll have x squared times p total minus kp, and that's equal to kp times p0. So x, I think I got that right, or did I mess up? So x turns out to be kp p0 over p total minus kp square root. Plus. Sorry, when I brought that over, it became positive. And that's what I got here. Okay, so now we have x. All I need to do is put it back into my original expressions. So for example, I want to find the pressure of PCl3. I just put my x back in, 1 plus x in the denominator, multiply by, p total, and that'll have it. So I do that, plot those together, and we get this result. So here's the equilibrium in this system as a function of the total pressure. Now notice when the pressure is low, then I've got more of the PCl3 and less of the PCl5. But as I squeeze it, then the reaction shifts to the left, and it crosses over right about here. And now we have more of the PCl5 and less of the PCl3. So that's what we told you in Gen Chem, is if you have a gaseous system, this one has A going to B plus C. If I were to squeeze that system, increase the pressure, it drives the reaction back to the left. Well, that just showed that in kind of in more explicit fashion. But it's far more controlled, because when you did it in Gen Chem, it was all willy-nilly. We didn't know the volumes, we didn't know the pressure, we didn't know anything in it. It wasn't very well specified. So, but this one is, just everything's ground. All right. The journalism coming. All right. Now, something that's interesting here. I'll go back to this Kp of 3.003. Now, what I did, and I went and calculated for the reaction what was the Gibbs free energy for the reaction at the beginning and when the reaction goes to completion. And I plotted that. So this is the result. Now, don't worry about how I did it. If you want to learn how to do it, take physical chemistry as one, of course. But what I did, this was at 10 bar. When I have all reactants, the Gibbs free energy is up here. When I have all products, the Gibbs free energy is right here. So as reaction goes from the left to the right, it begins to go, the Gibbs free energy drops, and it reaches a minimum right here. So that is where the system has settled. So the whole objective and that whole thing we started with is we wanted to find the smallest Gibbs free energy, or the largest entropy, if you want to look at it that way. I plotted it in a couple of different ways. It's this way, and here is just the Gibbs free energy change, so it reaches a 0 right about this point. Well, here's what's interesting. If I take and find that lowest point right here, what is the lowest G for the Gibbs free energy? I do that and calculate it. I come out with an x of 0.48055. If I put that back into the Kp expression, which is derived, put that x value in there, look at the Kp I get exactly the right Kp back again. So that equilibrium constant comes from the Gibbs free energy, and that just demonstrates it. So that was the whole point on that. Now, I'm not going to do this, but there is, if you want to see how it's done for a constant volume system, here's another reaction between N2O4 and 2NO2. I do it in a very similar way to what we had done in a constant volume, and I have a couple of plots there to see what the partial pressures are versus volume. And again, it fits what Chapier's principle in there. So anyway, now, turn into the homework. There's only 4 questions on this, so let's take a look at them. And of course, you're reading the questions to consider, and you're looking at all my comments. I reword a lot of different things, restate some of the things that I had done in there. But it first begins with, I have a reaction of carbon dioxide and hydrogen to produce carbon monoxide and water vapor. And so here we're just kind of go through the process. You're going to calculate the standard Gibbs free energy, products minus reactants, just as always. So you're going to get a delta G for the reaction, for this. So just go to the standard tables and look them up, products minus reactants, okay? And then from there, I want you to calculate the Gibbs free energy change for this reaction at the following non-equilibrium pressures. So this is essentially a general chemistry problem. We did this in Gen Chem, where you're using this. This is what we derived. Delta G0 plus RT times the natural log of Q. Well, of course, your Q has the same form as the equilibrium constant. So it's going to be the pressure of CO, the pressure of water, divided by the pressure of CO2 and the pressure of H2. Since each one of these things is divided by a 1 bar pressure, all the 1 bar pressures cancel out, and as is that. So what I'm just giving you some pressures. I give you 1.5 bars of CO2, 0.15 bars of hydrogen, and carbon monoxide, and so forth. Just put those in here, and then insert that value into here. Remember, Q is non-equilibrium, K is equilibrium. So you take your 298 Kelvin, right? You'll have the R and the T. You'll have a Q value. This you will have just calculated from standard tables, and then look at this and ask: is it greater than 0, or is it less than 0, or is it at 0? If it's less than 0, the reaction will proceed to the right. Greater than 0, back up to the left. 0, of course, is what we've been searching for. So A would be a very straightforward problem. Then I point out that at 960 Kelvin, the Kp for this reaction I give you is 0.534, and at 1260 Kelvin, it's 1.571. So I want to calculate the enthalpy of the reaction. Well, that is almost identical to what you did with vapor pressures. It is actually identical, we're just defining them differently. You're going to use this. That same form, the log of K2 over K1. I've given you Ks, I've given you Ts, you know R. So I'll simply solve for that delta H. Again, just get you warmed up, these are fairly straightforward. Then I want you to go and calculate. Now you'll get a delta H from this data. Then I want you to calculate the reaction enthalpy from standard tables. So you're going to do products minus reactants to get a delta H for the reaction. Okay? Compare the numbers and see how, if they're different, or are they slightly off, or are they identical, find out, and then kind of answer that question as to why you might think that to be the case. Okay? And then finally, in using your delta H that you calculated in D, and calculate the entropy change for the reaction, and calculate the Gibbs free energy in Kp. And so in other words, you're going to now go in the other direction. You get the delta H that you got from the tables. I've given you the literature values, so I want you to use that and calculate the Kp at 1260 Kelvin. So I want you to do it this way, though. So you're calculating get a delta G as delta H minus T delta S, and put that 1260 Kelvin? 1260 Kelvin in for this. Then get a delta G, and then do this. The Kp is e to the minus delta G over RT. That's how we got our Ks. But I want you to do it from this direction. So you get the delta H from standard tables, delta S from standard tables, put 1260 Kelvin in there, drop it into here, see what you get. Okay? And see how good or bad that number is. So then we can interpret that a little bit later after you got a chance to look at it. Okay? Then number 2, I've got an N2O4 NO2 reaction system. I've given you pressures and temperatures, so I want you to calculate the value of Kp at each temperature, and then the enthalpy of the reaction, and then the entropy. So what you're going to do is, since it's N2O4, going to 2 NO2, the Kp will, of course, be the pressure of NO2 squared, or actually pressure over P standard squared, divided by the pressure of N2O4 over P standard. You'll calculate a K. Now I've given you Ks or pressure values at 350 and 400 Kelvin. So you'll be able to calculate a K directly from that. Once you have done that, you can return to this once again and get a delta H for that. Again, it's got the same problem, very similar. But then I want you to calculate the entropy of the reaction at each temperature. This one's really fairly easy. If you recognize that those are equilibrium constants and your equilibrium conditions. So when you're working from this here at equilibrium, delta G is equal to 0. So that means that delta H is equal to T times delta S, and so your delta S will be your enthalpy that you calculated divided by the temperature. So you'll calculate the entropy change in that way. It's a 3-minute problem. Okay? So we're just looking at values, what they do, how they change, who's accurate, who's not, and then of course we'll discuss those a little bit later. There's always this temperature determinist type of problem. All right, so those kind of get you warmed up. Then we get to reaction 3, which is that extent of reaction problem. And we're going to do an Aber reaction, which is the famous one for producing ammonia. And I kind of get you started in H3. I get you started with this one in this way. We'll start with 1 and 3 amounts of that material. Okay? And so if that's initial, we'll start with 0 amount of this, then the change will be 1 minus x, and this change will be 3 minus 3x, and this will be 2x. Of course, this can be expressed as 3 times 1 minus x. Okay? So I get you started on that. Now, when you put this into, and I'll leave off the P naughts and all that, but I just want to point something out to you, is when you put this into a K expression, I just want to guide you mathematically what you're going to do. So you'll have to put the pressures and P naughts in there, but it's going to be 2x, well, let me do this more explicitly. It's going to be the pressure of NH3 squared, the pressure of N2, pressure of H2 cubed. You know this, okay? But if I put these values in, and this is why I did this. This ends up being 4x squared, that's 2x squared, 4x squared. This is I'm going to write it this way, it's a 1 minus x times 3 cubed times 1 minus x cubed. The pressure of hydrogen cubed is 3 cubed, which is 27, not 9, and 1 minus x cubed. Well, what that gives you when you do this is the following. You get 4x squared. This becomes 27, and it becomes now 1 minus x to the 4th. Okay? 1 minus x to the 4th. That makes it a perfect square. So what you can do, the way you'll solve this is, of course, equal to Kp. Bring the constants across. So you'll have x squared 1 minus x to the 4th is Kp times 27 over 4. Take the square root of everything. This is just a collection of constants. So you take the square root of this, that gets you this x. This will be 1 minus x squared. You can make it into a quadratic formula, a quadratic equation, and solve it in that way. But that's the trick to doing this one, is to put it in this form, take the square root of everything, and then you can finish up your arithmetic. All right, so it's a little more complicated algebra, but it's not bad if you should do it in that way. You'll see it should come out. I'll help you if you need. And that's what guides you through A, B, C, and D. And finally, we have the values from the results, produce an expression for the equilibrium constant in terms of x, P total, standard pressures, and all that. And then I gave you another graphic. I calculated it as well. It's identical to this, but it is for that reaction. And so what you'll do in the graphic that has the Gibbs free energy, you will go and you will estimate where the bottom of that curve is. It's kind of an obvious spot, so you can kind of see it. But take that and put it back, just like I had done here. Find out what that x is, put it back in your Kp expression here, and calculate a Kp and see if it comes out correctly. And you should find that it does. So you're redoing this for that particular problem. And again, the whole point of that is to tie in all the thermodynamics with what we were seeing, because that's where we came from. So that's what I have you do in E, calculate the equilibrium constants at 455 Kelvin, I have that. Then I had you do it from standard tables. So and I've given you values for the Gibbs free energy and the enthalpy. So I want you to do, calculate the Gibbs free energy, in other words, calculate the equilibrium constant in this way, then calculate it again using the K e to the minus delta G for the reaction over RT. Do it for that, compare the two, and they should be identical when you do that. And I've given you, like I said, G and enthalpy values to do all that. And you'll calculate the reaction enthalpy for the system. And then from that, I want you to calculate the Kp at 455 Kelvin and compare it to your estimated results. Because remember, because the Kp you're going to calculate from here is 298. So you're going to have to kick it up to 455 Kelvin. And you're going to have to use one of two equations. So you can either use this to calculate a second Kp at that elevated temperature, or you can use this one. I throw extra 5 points if you're bold enough to go for that one, if you want to.
For that one?
Huh?
5 points for that one?
Yeah, if you get the points for the problem, but I'll throw an additional 5 points on if you want to do that one. It's kind of like a bonus point. But they'll give you that option. We'll see how brave you are. And I've given you heat capacity values for everything, so you should be able to do that. Okay? So it's again, it's doing some work, doing some equilibrium work a little bit more precisely, and then accounting for proper things that we need. Okay, now, last part of this is where we're going to have to go next, because you know this question is coming on the exam. What are the assumptions that we are under here when we did this equilibrium constant and calculated the Gibbs free energy and everything? Well, we assumed that everything was a gas, everything was at 1 bar, and they were ideal behaving. So how does that apply to, like I said, I asked this earlier, a weak acid solution? You've been doing equilibrium constants for doing pHs and complexations and everything else under the earth. But how can you get away with doing that? Well, the answer is you can't, really. So what we're going to do this, if we have, of course, we started with the ideal gas law, where PV is equal to RT, the old famous Perkin law. And we worked from that. Now, if I change that, even by the smallest amount, and actually I do this, I get produce this down below. So if I did like this, here's the volume, RT over P, and I just added another alpha term in there. Well, this whole look, everything gets re-derived. That whole equilibrium constant expression that we love so much is gone, is vaporized. That products over reactants, equilibrium constant form goes away, and it becomes almost impossible to solve. So that is a real problem. So we have to figure out how we can get into real systems or non-ideal systems, and yet still keep that form of the equilibrium constant. That's our objective. Well, the way we do that is we start with the equation that got us the proper K. It looked like this: E standard plus RT times the log of K. We want that. We want to keep it. But instead of saying that this is going to be involving, ratios of pressures, we're going to define a quantity called the activity. Okay? And we're going to give it the symbol A. And so when I write a reaction, I'm going to see if I have an example. Like, for example, here, I have a reaction up here in the notes. H2 plus Cl2 in equilibrium with 2HCl. Okay? Now, we treat these as ideal gases. You write pressure HCl to the squared divided by the pressure of H and the pressure of chlorine, right? Just like a Gen Chem. But instead, here's what we're going to do. We're going to write a K this way. K will be written as the activity, I'll write a little a of HCl squared divided by the activity of H2 and the activity of Cl2. Okay, I write it in that way. Well, one problem comes about, well, how is this related to measured pressures? So we have to tie the two together. Well, we tie the two together by doing this. We say the activity of any component is going to be multiplied by a constant, or actually a coefficient called the activity coefficient, multiplied by the pressure. So for example, the activity of HCl will be the activity coefficient of HCl times the pressure of HCl. Now let's tie these two together and see what's coming on here. The pressure is what you measure. That's what's measurable. The activity is the thermodynamics. So when you do products minus reactants to get delta G's and calculate K's, then you're now using activities. So all we really need is to know what that number is. If I know what that number is, then I can go from this, which we love so well, and I can get to the pressures. Or having pressures, I can go to the thermodynamics. So this is how we're going to define it. The whole point is, how do we get to those? That's what we need to do. Now there's a bonus that comes out of this, because if we use this scheme, we're not even relegated to having to use gases anymore. Now it applies to solutions. The only thing that will change, and this will be our next topic, the only thing that will change is that the pressures will be replaced by molarities, or molalities, and that gets us back to what you were doing in Gen Chem. Now notice what happens. If the system is ideal, if it is ideal, then gamma is equal to 1. The activity becomes the pressure, and we do the same problems we've always been doing. So the farther away the activity coefficient is from 1, the more non-ideal it becomes. And we will need to do that. So we need to figure out how to use this. All right, and this is subject to your last homework problem, so let's see how we're going to apply this. Now first off, here I have some discussions in here. This still applies. No change there. That's good news. I can go to products minus reactants in the thermal table, I get K's. But I say, what is the activity? It is a thermodynamic quantity that connects the measured quantity. So pressures are measured, the activity connects us to the thermodynamic tables. So we define an activity, and for a gas system, we'll have the activity, there's my activity coefficient, multiplied by the pressure, and I divide by standard pressure to make it more properly the case. So again, a little discussion there. So how do we calculate it? Well, here's an example of how this might work. So here I've got a calcium carbonate and calcium oxide to carbon dioxide gas. Let's see how we would solve an equilibrium system here. I picked this one for obvious reasons, because that is a solid, and the calcium oxide is a solid, and the CO2 is a gas. You remember from general chemistry, when you're writing equilibrium constants, you do not include solids and liquids. So for this, the Kp is equal simply to the pressure of CO2 divided by the standard pressure. That's all, okay? Now, that would normally be the case if it were ideal. Now we have a new condition. This is ideal. Now we're going to have non-ideal. I'm going to write that Kp is equal to the activity of CO2. So that's now the answer. Now I'll use this over here now, and I will now rewrite this as the activity coefficient for CO2 times the pressure of CO2 divided by 1 bar, the standard pressure. Okay? So just like in an equilibrium constant problem, I would like to know, given a constant, what is the pressure, equilibrium pressure of carbon dioxide? So we need to do a little bit of work. Well, first I have the delta G's of formations for all the materials. So I have carbon dioxide, CaO, so I do a delta G for the reaction, which is products minus 3, where's that? Delta G. wrong number. There's the right number down here. I transcribed the wrong number up here. Sorry about that. But this, I got minus 394.4 plus a negative 604. So there's the products minus the reactants, which is negative 11.2. So I get a delta G for the reaction of 130.4 kilojoules per mole. So now I calculate a K from that, just as we've done. So I have a K Q is now E to the minus delta G over R. So I just do that, and I get a very, very, very small value. What's a little bit too small to get a nice equilibrium, 10 to the minus 23rd. That what it tells you is that this chalk doesn't spontaneously decompose very well at room temperatures. Duh. And of course, it vaporizes in my hand, crazy-wise. But anyway, that's a whole different reason. So what I need to do is now I need to calculate a K at a higher temperature. So I want it at 1500 kelvins, what I chose. So we now go back to this connection between equilibrium constants and the enthalpy. So I do that. So I calculated delta H for the reaction, products minus reactants. I put it in my formula. I now have my K at 298. E to the delta H, equation from up above, I have 298, and this is now 1500 Kelvin. And so I get a value now for KEQ 152.4. All right, that's a more substantial K. So at 1500 Kelvin, the chalk will begin to decompose. All right, so now let's solve the system. We now know what the K is. So, doing this, the K is, now what is it, 152.4. And off I go. I want to solve this for the pressure of CO2. Well, if I do that, the pressure of CO2 is equal to Kp times the standard pressure over this activity coefficient. Okay? So when this was 1, we had a really nice condition. Kp we would know, P naught is 1 bar, so the pressure would be 152.4 bar. But I need to know what that gamma is. So when I go in that, we produce that, but there's a problem. If I plot the activity coefficient, this is calculated, I get it from the full PChem course. Of course, you want to know how to do that, just take the PChem one, it's a wonderful course. Anyway, so if I look at the activity coefficient for carbon dioxide versus pressure, it varies dramatically. Way, way down at 0 pressure, it approaches 1. That tells you that as a gas goes to 0 pressure, it becomes ideal. But this then poses for us a problem, because I can't solve for the pressure of CO2 unless I know what gamma is, and I can't find out what gamma is until I know the pressure of CO2. In other words, I have to have the answer before I can find the answer. So that is a problem with this. So how do we get around that? Well, the way we get around that is through a recursion. What I will do is I will solve this system as if gamma were equal to 1, as if it's ideal. Solve the system. Then I will take my pressure that I get from that, I will go to my graphic, and I will find out what is the activity coefficient at that pressure. So we already can tell, look at this one here. If we assume gamma is 1 for this instance, then that's 1 bar, and Kp, that's 152.4. So I would come over here to about 152.4, look over here, and I see that the activity coefficient is about 0.38. Then I go back, put 0.38 in here, solve it again. Get another pressure, go back. Eventually you're going to go in and come back, go in and come back, and the pressures that you get out are going to be the same as the pressures that they're putting in. In other words, it will converge to a constant answer. So that's what we will do. Now, so first I say these steps solve for the pressure, assuming ideal conditions. And that's what I do. Here we set gamma to 1, so it becomes a 152 bar. And I say from the plot, we just pointed this out, at 152 bar it has approximate value, I pick 0.4. So now I put 0.4 back in here in place of that, and now I get 381 bar, different number. I now take that 381 bar, go get a new activity coefficient, which in that case is about 0.3, just an estimate. So I get in here, put it 0.3, and now I get 508 bar, and at that point, if I take the 508 bar, go back, that's going to now produce about the same numbers. So it will converge. So that is the correct answer. So there is the incorrect answer, so very, very non-ideal conditions. those types of pressures. So you find out the actual answer is about 508 bar. So that's how these activity coefficients work, and the last homework problem has you do that. Now, in the homework problem, I also had you do calcium carbonate and calcium oxide CO2, same problem. So I have you do exactly what I did here. From the thermodynamic tables, calculate the delta G standard and Kp for this reaction. Actually, it's on the notes. You can just copy them down. Then I calculate delta H for this reaction, and they're in the notes as well. I've done half this problem for you already. Let's pick a different one. Anyway, so calculate delta H, and now I'm going to have you calculate a Kp not at 1500 Kelvin, but at 1200 Kelvin. Okay? Then I say write down the equilibrium constant for this reaction in terms of activities. That's exactly what I did here. Having you do this. A, B, and C I've already done for you. Now we go, in this instance, instead of looking at a graphic, activity coefficients can be derived from certain equations of state. Remember, when we started off, we were parameterizing equations of state. Well, if you have those, you can produce expressions. So I've given you one. A gamma for this system, under certain given equation of state, is 1 over 1 minus a constant B times the pressure. And the B has a value, I've given it to you, of 0.05 reciprocal bars. So then I give you the steps. So I want you to go through this process. I want you to set gamma equal to 1, find a pressure. Take that pressure, come over to this, put it into here, calculate a new gamma. Take that gamma, put it back over here, get a new pressure, back and forth, until it converges. And it should converge about maybe 3 or 4 steps. So that's how you do a net recursion type of thing. So I outline that in bullet points. And of course, the last question is assuming gamma is 1, calculus, use the equation, and so forth. So that's going to be then our first non-ideal system that we will examine. Okay? Now, since we have this power at our fingertips, now we want to look at solution systems, since we can apply that in the same way. Then we can start looking at solubilities, weak acids, all those sorts of things. So we need to look at what do ideal solutions look like, how do we treat them non-ideal, and then a large part of that is how do we get that? Where do we get those from? And you'll be surprised where you've seen them before. You just didn't know that that's what they were before. There'll be more stuff to come. So anyway, we'll kill it off from there. And we'll begin that next section next time. We'll cut you out early. Go home.